All right, the next section is 15.4, part 2. This is triple integration in cylindrical and spherical coordinates. So far we've done double integrals in Cartesian and polar. We've done triple integrals in Cartesian. Now we're doing triple integrals in the three-dimensional analog, or analogs, sort of cylindrical and the analog of polar, which would be in 3 dimensions. The immediate analog of polar in 3D is cylindrical, and then there's this other coordinate system called spherical coordinates, which very similar to polar, but it is a little bit different. So, that being said, before we even get into the integration here, let's just take a minute to do a quick comment and recap of polar, cylindrical, and then eventually we'll talk about spherical. But let's talk about polar, and then we'll move into cylindrical. So let's just block that out for a second and take a look at what we have right here. So a quick recap here for polar. So polar is used in 2 dimensions. So here is a plane, 2 dimensions. Let's say x and y. And if you have a point in the xy plane, we can give it coordinates. In Cartesian, it would be x comma y, where this is the y value of the point, and that's the x coordinate of the point. Nothing new, nothing earth-shattering right there. Polar, we have this radius that extends from the origin. So important things to note are that the radius is always measured from the origin. So as soon as you set the radius, that doesn't fully tell you everything. Because if we just know the distance from the origin is whatever this is, well, really that could be any one of these points, a whole circle's worth of points. So to solidify which one of these points we're talking about, we also need to know what the angle theta is. So there's another thing here. And this would be the angle theta. Theta, the angle theta, is always measured from the positive x-axis. Or whatever the horizontal axis is, really. After this, what this means is that we can take this point x comma y, and it can be equivalently written as the polar point r comma theta. Now, how does Cartesian come into play? Well, for Cartesian, what we end up having, of course, we end up having three dimensions. So we have a z-axis now. And we're going to take our same picture that we had here, the same idea. If we're looking down, onto the xy plane, we have a point in the xy plane. That point can be labeled as x comma y, which is r comma theta, where r is the distance from the origin to the point, and theta is the angle that ray, or not ray, but that line segment forms with the positive horizontal. So here's our point, x comma y, which is equivalently written as, in polar coordinates, r comma theta. So we draw our same kind of picture, but in 3D, there's r, and this angle here is theta. But now, if we're in 3D, we have points that may have a non-zero z value, in which case, let's say we've got a point floating above the xy plane right here. So it's directly above this point. You can think of this point in the xy plane as the shadow of that point. So think of a flashlight shining light down. This point would cast a shadow directly onto the xy plane. We could also say that this point is the projection of a point x, y, z when z is 0. It's the projection onto the xy plane. So this point here simply has coordinates x comma y comma z. So this point in cylindrical coordinates is simply take the polar coordinates for the xy pair and then just tack on a z. So loosely speaking, cylindrical equals polar x squared plus y squared equals r squared. And then z, well, when you go from Cartesian to polar, z stays z. There's no change in z. So really, cylindrical is polar plus z.